All right, in this lecture, we're going to actually do the same problems that we have done in other lectures, but we're going to do them in a slightly different way. And this is an alternate way, and some of you might find it a little bit more clear than the original way you saw it. So let's begin. So here's one of them. And this here is known as a VIRP table because we have our voltage, our resistance, our current, and our power. So I did it in a different order. I didn't do VIRP. I did VRIP. I did VIRP, I think, on the other pages. Okay, so the V total, so the T's mean total, and those would be the equivalents also. So the V total is 10 volts because it's a 10 volt battery. And then I've labeled R1, R2, R3, and R4. So R1, R2, R3, and R4. Okay, so from that circuit. Now, the first thing that's going to be different is we're going to take this circuit and we're going to like stretch it out. So basically this is going to be like we have a multi-strand necklace, and here's the battery. We're going to open it up so that we can see what's in series, like each of the little pearls, and then what's in parallel, because there are multiple branches here in our circuit. So we're going to start at the positive end of the battery, and we're going to follow the current. And so the current runs into a 20 ohm resistor first. So then we have our 20 ohm resistor. And then the current, and then it gets to this spot right here. So it follows along, and then it's going to split. And some of it's going to go this way through the 30 ohm resistor. And some of it's going to go this way through the 50 ohm resistor. So see how it's split there? And then we're going to follow the current, and it's going to come back together again. It's going to come back together again. And then it's going to go through this 20 ohm resistor to the negative end of the battery. So we've taken this loop and we've stretched it out, and now it's easier to see that, oh look, those two there are in parallel, and then all of that is in series with each other. So we're going to take that parallel portion and squish it together. And so we're going to have 1 over REQ is equal to 1 over 30 plus 1 over 50. And we're going to get REQ for that is 18.75 ohms. So go ahead and pause and make sure you can get that. And then we're going to redraw, and then it makes it easier to see the redrawing. So we're going to have the long, and then we have the 20 ohm resistor that we had, and then we replaced that 20 ohm resistor, or the parallel portion, with the 18.75 ohm part. And then we still have a 20 ohm resistor. And then we have the negative side of the battery. Okay, and now it's really easy to see those are all in a line. And so we get an equivalent resistance of 20 plus 20 plus 18.75. So this is 58.75 ohms. Now that is going to go in for RT in our VIRP table. Okay, so then a lot of this is going to be where you know two things, you can find the third. Where you know two things, you can find the third. So we know these two things, so we can find the total resistance, or the total current. So V equals IR. We know it's 10 volts. And so we're looking for I, and we're going to use RT. So we're going to use things that are in the same column. 58.75 ohms. And we're going to get a current of, so this is 0.17 amps. And that's going to go in here for I total. Okay, and then the power is our ultimate check. So we can go P equals IV now. And we can go P equals 0.17 times the 10 volts. And so the power is 1.7 watts. So this is 1.7 watts. So when we are done and we've completed the whole VIRP table, which we are not done with, we should be able to add P1, P2, P3, and P4. P1, P2, P3, P4, and they should all add up to approximately 1.7 watts, and that's kind of like your ultimate check. And none of your powers can be bigger than 1.7 watts. So if you get more than 1.7 for any of these answers, you know you've done something wrong. So see, there's ways to check all along. Okay, so we solved for the current, the total current. That total current goes through this whole thing. So each one of these guys gets 1.7 amps. Now the yellow ones are our original drawings. So this here is R1. Okay, so this is R1 that we did right here, R1 that we did right there. This is 2 and 3 together, and this is R4. So we actually know the current through R1 now. Okay, the current through R1 is still that 0.17 amps. Okay, because if we are the current, let's zoom this out a little bit. Okay, if we're the current, we have to go through that guy. And then remember we split, and then we came back together, and we have to go through that guy. So that 0.17 amps goes through both of those guys. Let's put that back. So we know that I1's current is 0.17. And I4's current is 0.17. Okay, and so remember we said whenever you know two, you can find the third. So we know R and we know I, so we can find this voltage. We know R and we know I, so we can find that voltage. So that voltage, let's change colors so we know what we're talking about. V equals IR. See? Told you were going to V equals IR till the cows come home. Okay, so 0.17 amps times 20 ohms. So this is it's 3.4. Try to do it in my head. 3.4 volts. So this is 3.4 volts. And look, this one had the same current and the same voltage, so this is also 3.4 volts. Okay, so we're looking at this part right here. This is 3.4 volts. This is 3.4 volts. Now the current going through this is also 0.17 amps. So we can do the math here, and we can get that voltage, and that voltage comes out to 3.2 volts when you round it off. And look, they're all in series. And remember that when they're in series, that the voltages add up. So 3.4 and 3.4 and 3.2 add up to the 10 volts of the resistor or the battery. So since this is 3.2 volts here, since that's 3.2 volts, and that came from the parallel part, okay, that was what we put together, here. Okay, so that was these guys. And so each one of these is 3.2 volts. Each one has the same voltage. They're in parallel, they have the same voltage, and it's both of them are 3.2 volts. So now we know the voltage across R2 and R3. So we know each one of these is 3.2 volts. 3.2 volts. Okay, so we know 2, we can find the third. Okay, so V equals IR one more time, and we can solve for the current. So on this one, we're going to do 3.2 is equal to I times 30. And on this one, we're going to do 3.2 equals I times 50. So let's get that math. So this one came out to 0.11 amps. This one came out to 0.06 amps. And remember, they were in parallel with each other. And these two currents add up to 0.17 amps, just like they should. Okay, and then the ultimate check is to go and calculate all your powers. So pause and check to make sure you can get those. Remember, to find the power, we used P equals IV. So we 0.17 times 3.4 came out to 0.57. 0.11 times 3.2 came out to 0.35. 0.06 times 3.2 came out to 0.19. 0.17 times 3.4 came out to 0.58. And then if we take all of these and add them together, they should approximately equal 1.7. So we have 0.6, if we round it off, we could actually do the math. 0.58 plus 0.35 plus 0.19 plus 0.58. Hey, this came out exactly 1.7 watts. Woohoo! There's your ultimate check so that you know that you did it right. Now, when you go back and you look at your notes, you're not going to know what you did. So do you notice how I color-coded some stuff? Sometimes that makes life easy. When I redrew my circuit, okay, I color-coded that, and that matched the work that I was doing here. So sometimes that's helpful, but you want to make sure that all these things add up, or work out, sorry, not add up, and that things that should add up, add up. So these two currents added up because they were in parallel to this one. These have the same voltage because they're in parallel. Okay, this voltage plus this voltage plus this voltage, remember all these volts across, they were in series, and so their voltages needed to add up. So do the checks along the way before you get the whole VIRP table completed and then find out your powers don't add up, because that's very disheartening.
Okay, well, let's see. Anything else? Okay, well, short-ish meeting.
Yep.
Not too bad.
Thank you.
Yeah, let you guys get out of here unless there's anything else.
All right.
Okay.
Bye-bye.
Bye.
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 Hi.
Okay, so if we're going to stretch this one out, I'm going to do a lot less talking this time. Stretch this one out, start at the positive, and then we hit a node. So we're just going to go like this, and then we've got a node and it splits, and we've got the 100, which is R1, and then it comes back together, and on the other side of that is the 250, which is R2, and then it comes back together here, and then, oh look, it splits again, and it's 350 on this side, that's R3, and it's 200 on this side, and that's R4. And then we get back to, they come back together and go back to the battery. So that's it stretched out. Now when you look at it, the 100 and 250, those two are in parallel. And the 350 and the 200, they're in parallel. So we're going to squish those together, and then we'll have two resistors that are in series with each other, and then we'll take these two and add them together. And I'll show you the completed VIRP table. Okay, so this is the completed VIRP table. Now let's see if it makes sense. Okay, so R1 and R2 were in parallel with each other. So they should have the same voltage. Et voila, they have the same voltage. Okay, R3 and R4 are also in parallel with each other, so they should also have the same voltage. Okay, R1 and R2 are in parallel with each other, so the current through the 100 and the current through the 250 should equal the current through the battery. 0.12, 0.086, and 0.036 approximately adds up to 0.12, so that's good. And the same thing should happen here. Their currents should add up. 0.043 and 0.076 approximately add up to 0.12. So far, so good. The 8.6 volts and the 15.3 volts, because these two were in series when we boiled this down and we boiled this down. This came out to 71.4 ohms for this part and 127.3 ohms for this part. But the voltage across this whole thing and the voltage across this whole thing should add up to the voltage of the battery. So 8.6 and 15.3 approximately add up to 24. And then when we add up all of our powers, it does approximately equal 2.88. So I hope you tried to work this yourself, but you see how everything makes sense. All right, last one. So we're going to stretch it out. We're going to start at the positive. We're going to be the current, and the current gets here, and it splits. So we're going to start right away with a split. And then going through this branch, I have to go through both of those. So both R1 and R2 are on that branch. So R1 is 325. And R2 is 275. And then that comes back together. And then on the other half of that branch, so we did this half of the branch, on the other half of that branch, it's going to go through R3 and R4. So we're going to put R3 here and R4 here, and then they're going to come back together. So that's what it looks like when we stretch it all out. Okay? And then we don't need this guy anymore. And we can see that these two are in series. These two are in series. And then once we put those together, then these two here, okay, once we squish those two together and squish those two together, these are in parallel. Okay, so we'll make this one into one, we'll make this one into one, and then we'll squish those down until they're one. So 325 and 375 is 600. And then R3 and R4, 150 and 250 is 400 ohms. Okay, so I put those two together, and then I put those two together. I put these two together, 325 and 275, and then this was 150 and 250. So now they're in parallel, and then we do the 1 over thing, and we can get the whole equivalent resistance. So you try to work it out and pause the video, and we will compare our answers when we come back. Okay, so let's see if our answers make sense. Okay, so when we had our circuit, let's make this a little smaller so you can see everything I did. Okay, these two guys over here were in parallel, and they were the only thing in between the battery. So each one of those is 240 volts. Each branch is 240 volts. Now we can't put that in our table yet because there's two things on that branch. There's two things on that branch. So we don't know what R1 or R2 is yet. But we can solve for the current. And so now we can put the current in because the current through that whole branch is 0.4 amps. The current through that whole branch is 0.6 amps. And look, 0.4 plus 0.6 adds up to the total current of 1 amp because they were in parallel. So the currents need to add up to the current from the battery, so they add up. So that makes sense. And then when we put that current through here, we find out that 3 and 4 are 90 and 150 volts. And they're in series, so their voltages should add up, and 90 and 150 does add up to the 240. These guys' voltages should add up. 130 plus 110 is 240, yes. And then the ultimate check, when we take our powers and we add them together, whoop, they add up to 240. So it makes sense. And you are going to have an opportunity to practice it, but I hope that you find a way that works for you, but I am going to have you guys complete these VIRP tables. Okay, so don't put anything in the table until you know that it goes with that resistor. All right, we will practice this more next time I see you.